illustrating this principle and also expanding our context a little bit. Okay, we have a trapezoid representing speed in miles per hour. That would be the altitudes, graph altitudes, versus clock time in hours. Now, just because our speed is 75 miles per hour at the end of 3 hours and 65 at the beginning of 3 hours doesn't mean that the speed changed linearly from 65 to 75 miles an hour during a 3-hour period. But let's assume that for some reason or another that is what happened. Okay, this would not be a good model of what happens for somebody driving up a crowded interstate, for example. This could just be the coincidental time when they're slowed down a little bit, and here when they sped up a little bit too much. And the speed could change in any way between here and here. So it probably wouldn't be justified to connect these 2 points with a straight line and expect that you have any kind of a meaningful interpretation. However, let's assume that somehow it does. Maybe you start off and you're a little bit timid and you gradually speed up to 75 miles an hour and you're a little bit too aggressive, and that proceeds over a period of 3 hours, so you have more or less a linear increase in the speed. Okay, so, well, we can easily calculate the slope in the area, and I'm not going to go through the details of that. You should do that. You can do it in your head. And I think I said the speed in the area. I meant the slope in the area. Okay, hopefully you calculated these. The change in the speed is from 65 to 75 miles an hour. That's 10 miles an hour. You divide that by the 3, which represents the 3 hours, and you get 10 divided by 3, approximately 3.3. I rounded it off to the nearest tenth of a mile per hour, and it's miles per hour divided by hours, so that gives you miles per hour over hours. Now, I'll make a little note on that. Miles per hour means what? It means miles over hours. And it follows that miles per hour over hours is miles per hour or miles over hours squared. Now what about the area? Well, that one's really easy to calculate. The mean between 65 and 75 is 70. Multiply that by 3. That's 70 miles per hour multiplied by 3 hours. 70 miles over hours multiplied by 3 hours gives us 70 miles per hour, not miles per hour, 70 miles per hour multiplied by 3 hours gives us 210. Miles over hours times hours. Hours divided by hours is unity. We end up with miles. Okay, so that's very straightforward. Now, we'll look at another example in a minute. Okay, here's another situation. We have position as measured in miles, and let's say that's an odometer reading. You're driving a car someplace. So your position in miles is indicated by your odometer versus clock time in hours. Let's say it's a pretty new car. So you start out with 80 miles in your odometer and end up with 150. And of course, you might just have your odometer on trip time or trip mode. Okay, so what is the slope and what's the area of this graph, and what does each mean? You should work that out. Okay, the calculations are straightforward, although numbers are a little messier, and you might have well reached for your calculator to do this. From 80 to 150, the change is 70 miles an hour, and that corresponds to the rise of this trapezoid. And if you divide, or it's not 70 miles an hour, it's 80 miles, 150 miles, the difference is 70 miles, and that represents how far you travel, change in your position. And you divide that by 1.2, and I believe that comes out 58.83 repeating, which I rounded to 59, and it's going to have units of rise in miles divided by run in hours, miles divided by hours. So that's 59 miles per hour. The area, we take the average of these two graph altitudes. The average of 80 miles and 150 miles is 115 miles. 115, just to check, is 35 more than 80 and 35 less than 150, so that works. Add 80 and 150, get 230, divided by 2 is 115, which you should be able to do in your head. You should not be reaching for a calculator to do that calculation, but you might reach for your calculator to multiply 115 by 1.2, multiplying the average altitude by the width. You really probably don't need to. 1 times 115 is 115. 2 times 115 is 230. 0.2 then times 115 is 23, and if we can add 23 and 115, I believe we get 138. You can use your calculator to check me on that. You should be able to do that much mental arithmetic. If you can't, you're reaching for your calculator too much, and you should get out of the habit of doing that. However, getting that to accurate to the 100th of a mile an hour or whatever, don't expect you to necessarily do that. Okay, that involves fractions. 70 divided by 12 is 5, and 10 twelfths, 5 and 5 6, 5 6 is 0.83 repeating. Something should be common knowledge and so forth, but I'll get off my soapbox about that. Now let's talk about the interpretation of all these results. Okay, on the first graph, remember that our altitudes represent speeds, so our rise represents change in speed. Our run represents change in clock time, so we're dividing change in speed by change in clock time. That gives us the average ROC, rate of change of speed, WRT, with respect to clock time. And that's about 3.3 miles per hour every hour on the average, changed by 3.3 miles per hour. This is the average speed, which is the average altitude. The altitudes represent speeds, so the average altitude represents average speed, multiplied by the time duration. The DUR is supposed to stand for duration, and that kind of got cut off at the edge of the board. In any case, the average speed by how long it lasts, which is the time duration, gives us the distance, which is 210 miles. So both these quantities have meaningful interpretations. Now here, to get the 59 miles per hour, we divided the change in position by the time duration. Again, the altitudes represent positions, so the rise represents change in position, and the run represents the change in our clock time or our time duration. And that gives us average speed. How many miles divided by how many hours gives us our miles per hour. Pretty intuitive notion. This quantity represents the average of the two altitudes multiplied by the width. This is the area. The average of the two altitudes is our average position. That's 115 miles. That's kind of an important quantity maybe, but when we multiply it by the time duration, the change in the clock time, what does that mean? Well, it's meaningless, and the unit miles times hours in this context is meaningless. Okay, well, the implication here, or the lesson here, is that in the first example, the area interpretation was meaningful. That's because speed is the rate of change of position with respect to clock time. Speed is a rate with respect to clock time, and so this quantity is a rate with respect to this quantity. Therefore, the area was meaningful. In the second example, position isn't a rate of change of anything with respect to anything. Position is not a rate of change. It's a simple quantity. So when we multiply something that isn't a rate of change by the change in clock time or a time duration, we don't get a meaningful quantity, illustrating the statement we make here. In one case, the area makes sense because the graph altitudes were rates with respect to this quantity, and in the second, we had no meaningful interpretation because this quantity wasn't a rate. A couple of other brief observations that are worth thinking about. We don't know how the speed changed from here to here. This linear approximation might be valid, it might not. It could be that we stayed at 65 miles an hour until the last 20 seconds of this 3-hour period and then sped up to 75. Okay, then the 3.3 mile per hour rate of change of speed, average rate of change of speed, would be the average rate of change of speed, but it really isn't indicative of much of anything that happened for most of that 3 hours. Had we actually, at this point, all of a sudden hit our brakes for the last 10 seconds, we could have gone down to 50 miles an hour here, which would have given us a negative rate of change. So what happens in the last 10 or 20 seconds here could completely change this quantity. This means unless we have some good rate for expecting this quantity to have changed linearly, this quantity, while it makes sense as far as units and so forth, and could make sense if we do know that there's a fairly linear change in the speed, doesn't necessarily tell us a lot about what's going on, though. Okay, in this case, this 138 miles times hours actually depends a whole lot on where your trip mileage happened to start, assuming this is, let's say, a trip mileage. If you had started at 20 miles and ended up at 70 miles later at 90 miles, you would have gotten the same result here because you would have had the same change in position, but this result would have been quite a bit different, okay? Or if you'd started at 760 miles and ended up at 830 miles. Again, this would have been the same, but this would have changed. But the actual behavior of your automobile during the trip, the average, and everything that happened during the trip would be the same no matter where you started the trip mileage. Okay, the only difference would be in what your odometer happened to read. So this quantity depends on just a couple of coincidences of where the trip mileage happens to be. So it's not a very indicative quantity. Just another reason why we say that that quantity is pretty much meaningless.